Alright, this screencast is going to talk about addition polymers. First objective is to describe and explain how the properties of polymers depend on their structural features. So, if you remember from the organic unit, polymers are made primarily from alkenes. The double bond here kind of breaking and forming a bonding site for another monomer. Structural features of a polymer are going to be the chain length, the structure of the monomer, the branching, and also the orientation of the side groups. So we can have a very simple monomer, ethene, forming a very uniform polymer, polyethene. We have propene here, and remember we can draw it as a bent so that it's easier to see what the repeating unit would be. And you can see that there's this methyl group that would make this polymer, polypropene, different than the polyethene. Then we have chloroethene with this chloride ion, or chloride atom I should say, sorry, forming the polychloroethene, also known as PVC, and then the styrene with this hexyl group, forming a polystyrene. So branching. Polyethene can be produced under different conditions. There's a low density polyethene. This would be polymerized under very high pressures using a free radical mechanism. This low density polyethene, and if we just go back real quick to look at the polyethene, it would look like this. Okay, so the low density polyethene is used in plastic bags and plastic wraps, so it's pretty flexible, not very strong. Then there's a high density polyethene, and that's polymerized at lower temperatures using a catalyst and an ionic mechanism. These are used for plastic buckets and toys. So the high density is a stronger, more brittle, less flexible kind of polymer or plastic. So where do the differences come into, or what are the differences between the low density and the higher density? And if you look at this low density, you see that the branched polymers are very disorganized with fairly weak intermolecular forces between the polymer strands. Contrast that structure to a high-density polyethene where you see the regular structure of the polymer chain, very ordered structure with more ability for these intermolecular forces to form between these chains, meaning a stronger intermolecular force holding the different polymer chains together. Now let's take a look at the side groups. Here we have polypropene. This is the repeating unit. The N, by the way, the number of units this is, really depends on the reaction conditions. Okay. But generally that N is somewhere in the thousands, and that's generally speaking. Here we have two different forms that can form with the polypropene. This is the isotactic form, and if you notice using this 3D structure that all of the methyl groups are oriented in the same plane with the hydrogens in another plane. This is fairly ordered, and it's produced with the ionic mechanism. We contrast that to the atatic form, and these are when they are randomly oriented. Okay, so you can see that not all of the methyl groups are in the same plane. Some of them are going away from you, some of them are coming towards you. Hopefully you would expect that the properties of these two different types of polymers would be different. We have crystalline polymers. These form very orderly structures. That would be the isotactic polymers. And those make the polymer tough and strong because, again, you're going to have this regular pattern forming, crystalline region here. An amorphous polymer is formed from branched or less orderly structures, like the atactic polymers. And those, because it's going to be more disordered, would be more flexible as a substance. If we go back just briefly to this slide, okay, the isotactic form is tougher, and it can be molded into different shapes. Things like bumpers and toys. Okay. This can also be drawn into fibers. Into fibers, and can be used in clothes and carpets. The less ordered but more random is properties are more flexible, softer. These are sometimes used as sealants and waterproof coatings. Going on and talking about how are we going to modify the properties of addition polymers. We can use plasticizers, we can use what's called blowing agents, and we can cross-link polymers. If we look at the PVC, polyvinyl chloride, again this is the repeating unit, it has this large polar chlorine atom. It is hard and brittle. But what we can do is we can add a small molecule. Okay? And what happens is these small molecules kind of fit between these organized chains of polymer, and they serve to increase the flexibility and reduce the brittleness. They give a little bit of play into the substance. Looking at another polymer, we have polystyrene. Your styrene, free radical vinyl polymerization, this would be your repeating unit. This polystyrene is colorless, transparent, and brittle. If we add a volatile hydrocarbon, such as pentane, into the polystyrene beads, and then we place it in a mold and heat it, that pentane is going to vaporize, and it creates bubbles in the polymer, and it causes it to expand. This changes the colorless, transparent, and brittle polystyrene into a less dense, opaque white, and thermal insulator. And then we have cross-linking. Defining two terms, there are thermoplastic. These are polymers whose chains are held together with intermolecular forces, and when they are heated, they soften, and that allows them to be remolded into different shapes. There's also a thermosetting. When a different type of polymer is heated, two different polymers form cross-linkages, and that adds strength and stability. It's more of a structure to the polymer. These cross-linkages are covalent bonds. So once those are formed, they're not going to be able to be remolded, right? So this thermoplastic material can be remolded, whereas the thermosetting, it's pretty much a permanent change to the polymer. So here's the thermosoftening polymer, and that's it in the form of a fiber. Here it's attempting to show what those cross-linkages, those covalent bonds look like in a thermoset polymer. Then we have the vulcanization of rubber. This is natural rubber. It's a long chain. But if we can take that and add some sulfur to it, it forms these cross-linkages, forming a more tough and hard rubber that's used for like tires. So what are some of the advantages and disadvantages of polymer use? Advantages, there's a wide range of properties. Low density, moldable. You could go on forever because you're really talking about plastics, and if you think about our world, there's so many different types and uses for plastics. Plastics are typically chemically unreactive. They're cheap to make. Some can be recycled and reused. Here's a table of different uses for the different polymers. Again, that polyethylene, the low-density plastic bags, clean film, electrical insulation, the high-density, more rigid buckets, plastic toys, water pipes, crates. Looking at PVC, there's a rigid PVC that's electrical insulation, water pipes, and floor tiles. And then we have flexible PVC, which is that thermoplastic, low tensile strength and density, used for raincoats and cling film. Polypropylene, the atactic form, soft and flexible, used in sealants and roofing. The isotactic, the more ordered form, automobile parts, plastic ropes, carpeting, clothing. Then we have the polystyrene, hard and transparent, used in rigid boxes, television and radio cabinets, toys, imitation glass. The expanded form, meaning where you put that vaporizable component in there, it makes bubbles. This is used for disposable cups, insulation, and packaging. And then we also have Teflon, highly water repellent, extremely low friction. That's used in nonstick pans and like Gore-Tex fabric. What are some disadvantages to the use of polymers and plastics? Comes from the feedstock crude oil. It's a natural resource, and at some point we will use all of that resource up. And there are also disposal issues. Landfill, incineration, and recycling are ways to deal with the vast amount of plastic that we use. Looking specifically at the landfill, it's easy and you can deal with very large volumes of plastics. The negatives about putting plastics into landfills is that they aren't typically biodegradable. And in the landfill, when things degrade or decompose, usually it needs air. Landfills typically are anaerobic because there's just piles of stuff and the air doesn't get to the bottom. That type of decomposition also produces methane and land use. With all the landfills, we do just keep using up land space to put our trash. They are coming with biodegradable plastics now, using biodegradable things or biodegradable plastic. They use small particles of natural polymers such as cellulose, starch, and protein. And as the enzymes break these natural particles down, the bags do fall apart. How about burning it? Well, positives is it does reduce the amount of plastics, the volume, and it does provide an energy source. The negatives to burning plastic is it produces toxic gases and greenhouse gases, and does have some leftover toxic substances that then have to be landfill. And then there's also recycling. Positive, it conserves natural resources. The negative is sometimes the process to recycle it is complicated, and it can cost a lot of money to recycle plastics.